Hi everyone, we are Paola, Danica and Regina. Today we're answering the burning questions like how does a simple bag save you in milliseconds?
It's not magic, it's chemistry. Specifically, it's about very fast explosive reactions. We analyze the thermodynamics behind car airbags, and the results are very intense.
Exactly. We're going to break down the reactions, the math, and the safety behind the steering wheel. Let's dive in.
So, question number 1. How do airbags work chemically? It starts with a crash sensor. When a collision is detected, an electric igniter fires up a solid mixture inside the inflator.
And that tires out to start the reaction, the decomposition of a sodium acid.
Right, in our document we calculate the primary reaction. 2Na3 turns into solid sodium and nitrogen gas.
The nitrogen gas is the key. It expands incredibly fast to inflate the bag. We found that the change of the entropy is positive, around 483 joules over Kelvin. This is huge jump in entropy. Basically, it means we are going from the small solid to a massive amount of chaotic gas instead.
Okay, but is this reaction hot or cold? And how much stuff do we actually need?
It is definitely hot. We calculated the enthalpy and found out to be negative, minus 43.42 kilojoules for the reaction. That means it's exothermic. It releases heat.
This heat is actually used because hot gases take up more volume, helping the bag to inflate faster.
To make this realistic, we can run the numbers for a standard airbag containing about 100 grams of sodium acid.
Based on the molar mass of 65 grams mole, 100 grams is about 1.54 moles of rectal.
When you run the Stoichiometry, that its 100 grams released approximately 33.4 kilojoules of energy, and it's a lot of energy released in the fraction of a second.
Yes, it is, and it's highly reactive and unstable. That's why the airbag isn't just sodium acid. It's the three-step chemical recipe.
Exactly. We call these like second neutralization reactions. The system uses a potassium nitrate and silicon dioxide, which is basically a sand to clean up the mess.
The dangerous sodium reacts with the potassium nitrate to form oxides, and then those oxides react with the sand to form alkaline silicate,
which is essentially harmless powdered glass, so the engineering ensures that toxic raw ingredients turn into safe, stable waste.
So, how does this actually save lives?
It comes down to exponentially. We calculate the Gibbs free energy and got the negative number minus 187.56 kilojoules.
A negative free energy of Gibbs means that the reaction is spontaneous. In fact, we calculated that it is spontaneous at any real temperature, whether you are in the freezing mountain or a hot desert. If that sensor trips, that bag will explode to save you.
Finally, what about the environment? What do we do with the waste?
The gas is released. The release is just nitrogen. It makes up the 78% of the air that we breathe. So that's the totally harmless.
The concern is the solid residue. Since it contains silicates and metal remains, it shouldn't just be dumped in nature.
The best disposal method is professional recycling, where the metal parts are separated and the glassy residue is treated as industrial waste, preventing soil contamination.
So the next time you get in a car, remember there is a mini chemical plant in your steering wheel, waiting to protect you.
It's perfect balance for thermodynamics, stoichiometry, and safety engineering.
For me, the most impressive part was seeing how thermodynamic numbers directly translate to safety. We calculate negative Gibbs free energy, which proves mathematically that this reaction is spontaneous at any temperature. It gives me a lot of confidence knowing that the chemistry is designed to work instantly, whether it's freezing or hot outside.
What stood out to me was the power of precision. Through our stoichiometry calculations, we saw that the relatively small amount of reactant, just 100 grams, can make massive volume of nitrogen needed in milliseconds. It proves that stoichiometry is just not theory, it's essential for the efficiency of the design.
I was struck at the smart design of how chemically mixture. It's not just about the explosion, it's about controlling it. Seeing how the system uses the secondary reactions really shows how chemically engineering solves problems to keep users safe.
Thanks for watching.